Hi, my name is Vanessa Myhaver. I'm an applied math master's student at the University of Vermont, focusing on chaos and dynamical systems. I've been working with my advisor, Dr. Jeremy Schnittman from NASA Goddard in the Gravitational Astrophysics Lab, and this is my presentation on Resonant Trojan EMRIs with LISA. EMRIs, or extreme mass ratio inspirals, are a system in which a stellar mass black hole is within the accretion disk of a supermassive black hole. The gravitational waves produced by this system serve as a precision probe for the spacetime curvature of the system. These systems are prospective gravitational wave sources for the detection of observational signals from LISA, which lead to our objective of this research, which is to model the dynamics of and calculate the waveforms from Trojan analog EMRIs. These are multiple EMRIs within a single system. So looking at the top right figure, we have two stellar mass black holes within the accretion disk of a supermassive black hole. For this research, we will lock those two stellar mass black holes into one-to-one resonant orbit analogous to that of Jupiter's Trojan asteroid system. So looking at the bottom right figure, we have the Sun, Jupiter, and their 5 Lagrange points. The L1 through L3 Lagrange points are unstable, and the L4 and L5 Lagrange points are stable. This is because the L4 and L5 Lagrange points create an equilateral triangle with the Sun and Jupiter. So we have one equilateral triangle from the L4 point, the Sun and Jupiter, and then a symmetric system with the L5 Lagrange point. For this research, our analogous system will be that such that the supermassive black hole will be in the location of the Sun, and the two stellar mass black holes will be locked in the position of Jupiter and the L4 Lagrange point. From this, we hope to identify unique features from gravitational waves of resonant Trojan EMRIs compared to that of single EMRI systems. We hope to receive good enough signal of systems such as this from LISA. In order to do this, we set the initial conditions of each of the three bodies, meaning the mass, positions, and velocities. We then calculate the three-body problem equations of motion, which are on the right. By taking the initial position and velocity, we then calculate the position, velocity, and acceleration at each time step using a numerical method to then determine the future position and velocities of each time step. Getting the resulting position matrix, we're able to model the dynamics of the three bodies within the system and calculate the gravitational waves of the system. We use the quadruple moment, which is on the bottom left, and the quadruple formula, which is on the bottom right. By using the position matrix, we calculate the quadruple moment, then place this into the quadruple formula, which allow us to produce the gravitational waves of the system. Using these methods, we have two main results of orbits, the first being the tadpole family of orbits. Looking at the figure on the left, we have the position projection, which is the dynamics of the three bodies within the system. We have the supermassive black hole in the center, and the two stellar mass black holes starting at their initial positions of the prospective Jupiter and Lagrange point locations. As you can see in this, they divert very little from that of their initial positions. This is because we have set the initial position and velocity of these two bodies to do as such. As well as diverting very little from this point, we then have the two stellar mass black holes co-rotating around the supermassive black hole counterclockwise. From these dynamics, we can then calculate the gravitational waves of the system. As we can see in the top right corner, we have the gravitational wave plot, which is just about a perfect sinusoidal curve. We then take the Fourier transform of the gravitational wave to calculate the libration frequency, which is in the bottom right-hand corner. In this plot, we identify one main peak. This is at 2 times that of the orbital period of the system. This is such that the two stellar mass black holes are co-rotating around the supermassive black hole. Because there is very little diversion of the two stellar mass black holes from their initial positions of that analogous Jupiter and Lagrange point location, this system is very similar to that of what we would receive from a single EMRI system. By slightly adjusting the position and velocity of the initial conditions, we can then divert the two stellar mass black holes from that of the initial positions of Jupiter and the Lagrange point. So as you can see in the left figure, the position projection, we have the two stellar mass black holes tadpoling or ovaling around those positions of Jupiter and the Lagrange point. These two stellar mass black holes will then again co-rotate around the supermassive black hole, creating a separate libration dynamic. We can then calculate the gravitational wave of the system, which is again in the top right-hand corner. As you can see from this plot, it's very different from that of the perfect sinusoidal graph that we saw in the previous slide. We then again calculate the Fourier transform of the gravitational wave to receive the libration frequency plot below. In this plot, we identify three main peaks. The center highest peak represents that 2 times the orbital period of the system, so the two stellar mass black holes co-rotating counterclockwise around the supermassive black hole. We then have the two higher peaks around it, which are in the location of 1 and 3 times that of the orbital period of the system. These represent the moments in which the two stellar mass black holes are closest and furthest from each other. So not only can we identify the rotation of the stellar mass black holes around the supermassive black hole, but we can also identify the motion of the two stellar mass black holes in reference to each other. The second family of results we receive are the Horseshoe Orbit family. I mentioned earlier that we can adjust the position and velocities of each of the bodies in order to identify different libration frequencies, but we can also adjust the mass ratio of the two stellar mass black holes to identify different dynamics of systems. Here I have given 3 examples: the 1-to-1 mass ratio of the two stellar mass black holes, meaning they have the same mass. We then have the 2-to-1 mass ratio in the center, in which the mass of the stellar mass black hole 1 is twice that of the stellar mass black hole 2. We identify the dynamics such that you can see the stellar mass black hole 2 has twice the width of that of black hole 1. This will continue for any mass ratio, such as the 3-to-1 mass ratio, where black hole 2 has 3 times that the width of black hole 1 dynamic. This will continue on for any mass ratio of the two stellar mass black holes in comparison to each other. Looking more closely at the Horseshoe Orbit family, on the left we have the position projection of this system. This is the 2-to-1 mass ratio of that two stellar mass black hole, of the two stellar mass. Looking more closely at the Horseshoe Orbit family, we have on the left the position projection of that 2-to-1 mass ratio of the two stellar mass black holes. In the center, we have the supermassive black hole, and surrounding it, we have the two stellar mass black holes. The stellar mass black holes will start in their respective locations of the analogous Jupiter and L4 Lagrange point locations. They will then horseshoe down to the bottom left-hand corner, where they will meet at their first closest approach point. They will then horseshoe back to the right-hand side, where they will meet at their second closest approach point. While following these dynamics, they will also co-rotate counterclockwise around the supermassive black hole. From these position dynamics, we can then calculate the gravitational wave of the system, which is on the top right-hand corner. As we can see in this plot, this diverts very greatly from that of the perfect sinusoidal graph that we saw that represents the single EMRI system. The peaks in this plot represent the points where the two stellar mass black holes are at their closest and furthest approach points. We can then take this gravitational wave plot, calculate the Fourier transform of the gravitational wave to receive the libration frequency of this system. In the bottom right-hand corner, we have the libration frequency plot, which we can identify has 3 main peaks. The center peak, again, is that 2 times the orbital period of the two stellar mass black holes surrounding the supermassive black hole. We then have 1 and 3 times the orbital period of the system, which represent the closest and furthest approach points of the two stellar mass black holes, so we can identify the dynamics of the two stellar massive black holes in reference to each other. From these unique features in our results, I will continue this work as my master's thesis at the University of Vermont while working with Dr. Jeremy Schnittman from NASA Goddard and Dr. Chris Danforth from the University of Vermont. We will transition to post-Newtonian equations of motion, then calculate the gravitational wave losses to identify when we would receive signals from a system such as this and when a collision could occur. We will also simulate realistic gravitational wave signals expected from LISA given similar EMRI systems. I would like to say a huge thank you to my mentor, Dr. Jeremy Schnittman, and I'd also like to thank you all for listening.